Hey everybody, here is the companion video for homework number 4. I would also point out that there is an additional video from the last time I taught pre-calculus covering this material, which is longer but in front of a classroom, but is a little more animated and has more examples. And there's also the video that Grant shared that I would also recommend watching. So if you want more sources, those are great places. They're right in Canvas underneath this video. All right, let's talk about the logarithm rules. There are 3 rules for logarithms. And sorry, I'm at home and I feel like the quality is not as good here. But anyway, there are 3 rules for logarithms. The first one is that if you take the logarithm of a product, so log base b of x times y, you can break that up as log base b of x plus log base b of y. In a similar way, log base b of x divided by y is equal to log base b of x minus log base b of y. Finally, thirdly, the logarithm of x to a power doesn't matter. Again, none of these, the base can be any positive real number. It's not 1. Here, log base b of x to a power is the same or equal to p times log base b of x. We often call this the product rule, the quotient rule, and the power rule for logarithms, but I don't like to use those names because when you take calculus, you learn a product rule, a quotient rule, and a power rule for derivatives. And those are the things that, like, when people say the power rule, that's what they actually mean. So I won't use those here. I would encourage all of you to check out some examples of this on your own. So like when you have a second, I would encourage you to look at, say, like log base 2 of 4 plus log base 2 of 8 and see how that simplifies into exactly what it should using this. Similarly, you could look at, say, log base 3 of 81 minus log base 3 of 9 to see how this second rule kind of works. And you can calculate those, right? Log base 3 of 81 is 4, log base 3 of 9 is 2. And then thirdly here, for this one, you can look at something like log base, sure, 5 of 5 to the third. And think about how that should simplify using this rule, or just what it should be using our rules for logarithms, or our logarithm knowledge. So I would encourage all of you to try that on your own and see kind of the, oh yeah, this is going to be log base 2 of 4 times 8, which is log base 2 of 32, which is 5. This is going to be log base 3 of 81 divided by 9, which is log base 3 of 9, which is 2. This is going to be log base 5 of 5 to the third, which is just 3, or you can think about bringing 3 down in front and saying it's log base 5 of 5 times 3, which is 3 times 1. So getting into some examples here, we want to evaluate some things. So if I want to evaluate log base 3 of 9 to the 5th, I'm going to say that log base 3 of 9 to the 5th is equal to 5 times log base 3 of 9. Then we kind of just know that log base 3 of 9 is 2. You can also write it as log base 3 of 9, sorry, log base 3 of 3 squared. It's going to be 5 times 2, which is 10. That's how you do it using this rule, or you could kind of go back to what we know. We could say, oh yeah, I know that this is log base 3 of 9 to the 5th, and I'm going to set it equal to x. You could rewrite it as 3 to the x equal to 9 to the 5th. You could write both sides as powers of 3. This is 3 to the x. This is 3 to the 2nd to the 5th. So then you're going to be getting 3 to the x equals 3 to the 10th. So x has to equal 10. But this feels like kind of a faster way of getting there, where you don't have to rewrite this equation as an exponential equation and then solve. Either way is fine. Natural log of 13, well, the natural log of e to the 13. The natural log of e to the 13 is 13 times the natural log of e. And it is important to remember that the base of the natural logarithm is base e. So this is just going to equal 13 times 1, because you have log base e of e. But if you like, it's okay to rewrite this as 13 times log base e of e, and then of e, sorry, getting ahead of myself there. And then log base e of e is just equal to 1. This is going to be 13 times 1, which is 13. Let's look at some more examples. Sorry, I feel like my paper's a little bit cramped here. So, solve for x, where the equation is log base 2 of x plus 3 minus log base 2 of x minus 4 equal to 3. So the first thing we're going to do whenever we're trying to solve a logarithmic equation is if we have multiple logarithms, we're going to compress them using those log rules. I'm going to show them to you again. So just as a reminder, I have that log base b of x divided by y is equal to log base b of x minus log base b of y, and vice versa. If I start with log base b of x minus log base b of y, I can write it as one logarithm, log base b of x divided by y. So I can write this left-hand side as log base 2 of x plus 3 divided by x minus 4. So that's what we're going to do first. We're going to rewrite this as log base 2 of x plus 3 divided by x minus 4 equal to 3. And then we're going to rewrite this logarithmic equation as an exponential equation. So we're going to say 2 to the third power equals the stuff inside the logarithm, which is in this case x plus 3 divided by x minus 4. And now we're just solving a rational equation. So we're going to multiply both sides by x minus 4. We're going to get 2 to the third, which is 8 times x minus 4 equal to x plus 3. We're going to distribute the 8 there. We're going to get 8x minus 32 equal to x plus 3. We're going to subtract x and get 7x. We're going to add 32, and 32 plus 3 is 35. And then we're going to divide both sides by 7 to get x equal to 5. And that's our answer. You can even check it if you want. Plug in 5 here. Log base 2 of 5 plus 3 is log base 2 of 8, which is 3. And here, if you plug in 5, 5 minus 4 is 1. Log base 2 of 1 is 0. And 3 minus 0 is 1. It's 3. Saying a lot of wrong things today. Sorry about that. Okay. That said, actually, I won't say that. So, problem 4 here, or number 4. Solve for x again. This time it's a natural log of something equal to 2. So here, if we're going to rewrite this, it might help us to write it as first log base e of some stuff equal to 2. And then we're going to rewrite it as your base to your power equals the inside stuff. This one's not going to simplify quite as nicely, but we're still going to solve for x. Multiply both sides by 7 to get 7 times e squared equal to 6x plus 1. Subtract 1 from both sides. So you get 7e squared minus 1 equal to 6x. And finally, divide both sides by 6. So that 7e squared minus 1 all divided by 6 is equal to x. And that is our final answer. It cannot be simplified any further. You could plug this into a calculator to get an approximate value if you care to, or if you're asked to. So just plugging this into a calculator real quick here, so you can see this. I would probably do e squared first. So there's my e to the x, and then plugging the 2. E squared is about 7.3, and then I'm going to multiply that by 7. I'm going to subtract 1. I'm going to divide by 6. So if I was asked for an approximate value, I'd write approximately something like 8.45. But I'm almost never going to ask, I wouldn't say never. Occasionally I do ask for an approximate, a decimal approximation. So it's good to be able to use a calculator to get that. All right, let's look at some more things. Solve for x. So if I want to solve this equation for x, I've got log base 3 of log of x equals 0. I'm going to start rewriting this as an exponential equation. So what I'm seeing here is log base 3 of some stuff equal to 0. So I'm going to rewrite this as, if I'm looking for the outside in, base is 3, my power is 0, and it's equal to whatever my finger is covering up here. So we're going to get 3 to the 0th power equals log of x. 3 to the 0th is 1. So we have 1. And I'm going to rewrite log of x. Well, I didn't write a base, which means the base, if it's a log log, it's log base 10. And then I'm going to rewrite this again as an exponential equation. It's going to be 10 to the 1 equals x, which means x equals 10, or 10 equals x, either way. Yeah, cool. All right, simplifying using log properties. Son of a gun. Sorry, my camera is being very finicky. I apologize about that. For my really excellent use of son of a gun there. Also for my giant face in your face. Okay, back we go. I'll try not to bump the cord here. Jeez. All right, so simplifying using log properties. Let me click on this so it doesn't look quite so terrible. There we go. So simplifying things using log properties. Sometimes things happen nicely, meaning here I've got log base 6 of 4 plus log base 6 of 9. I'm going to write that as log base 6 of 4 times 9. And then I'm going to see if I can simplify that further by saying, oh, look, that's log base 6 of 4 times 9 is 36. And 6 squared is equal to 36. So log base 6 of 36 is equal to 2. What's interesting is if you plug this into a calculator, log base 6, in fact, log base, oh, you can't do log base 6 to the 4th, right? Log base 6 to the 4 is not a nice number. It's like, it's a decimal less than 1 that doesn't get nice ever. Same deal with log base 6 to 9, right? That's a decimal is a little bit bigger than 1 that's never really going to be very nice. But together they perfectly add up to 2, which is kind of neat. Yeah. Let's look at another one here. Again, using these log properties. Sorry, you can't quite see that. Using log properties to simplify the expression log base 2 of 120 minus log base 2 of 3 minus log base 2 of 5. So the bigger thing to see here is that when you're adding or subtracting logs together, all of the arguments of the logs with positive coefficients end up in your numerator, and all the logarithms with negative coefficients, the arguments end up in the denominator of the final argument. So a couple ways to do this is to write this as, I'm just going to combine these two first and get log base 2 of 120 divided by 3 minus log base 2 of 5. And I would normally just simplify 120 divided by 3 as 40. In fact, I probably still will. So I'm going to write this as now log base 2 of that number 40 divided by 5. 40 divided by 5 is 8. Log base 2 of 8 is probably my favorite example. That's going to be 3. I should mention, though, if we just jump straight to the conclusion, then we're going to get log base 2 of 120 divided by 3 times 5. Again, using that kind of rule of thumb, I said that if you have a positive coefficient, the thing ends up in the numerator. If you have negative coefficients, those things end up in the denominator. They still work out the same. 120 divided by 3 times 5, well, 3 times 5 is 15, and 120 divided by 15 is 8. That's going to be log base 2 of 8 once again, which is again equal to 3. So you really can kind of just say, oh yeah, all the things with negative coefficients, their arguments end up in the denominator, and all the things with positive coefficients, their arguments end up in the numerator. All right, let's look at this example. Solve for x, where we have log base 3 of x minus 4 plus log base 3 of x plus 2 equals 3. So again, like I said before, when you have a logarithmic equation and you have more than one logarithm, you want to combine those logs using either the product rule or the quotient rule, where the logarithm of a product is equal to the sum of the logs. So the sum of the logarithms is going to be the logarithm of the product x minus 4 times x plus 2. So here we're going to say that log base 3 of x minus 4 times x plus 2 is equal to 3. Then we're going to rewrite it as an exponential equation. So our base is 3, our power, so it's going to equal this. So we're going to have 3 to the third equals x minus 4 times x plus 2. We're going to multiply out the right-hand side, and we're going to simplify the left-hand side. So 3 to the third is 3 times 3 times 3, which is 27. And this is going to be x times x minus 4x plus 2x minus 8. We're going to bring everything to one side and also combine like terms. So we're going to subtract 27 on each side to get 0 on the left. Negative 8 minus 27 is negative 35. So we're going to get x squared, and then minus 4x plus 2x is minus 2x. And then again, minus 8 minus 27 is minus 35. This does factor, and problem sets like this, if they're set up well, usually do. We get 0 equal to x minus 7 times x plus 5. So our possible solutions, I do want to emphasize the possible here, is either x equal to 7 and or x equal to negative 5. I will say generally for logarithmic equations like this, Both of these things can actually be solutions, or one of them is actually a solution, or neither of them are actually a solution. So we have to go back and test. And here's the deal. We're not so much just testing to see if it works, we're testing to see if the numbers we've gotten are in the domain of the original expression. So if I plug in 7, I get log base 3 of 7 minus 4 is 3, plus log base 3 of 7 plus 2 is 9. I don't actually care that it adds up to 1 plus 2, which is 3, although it's good that it does. But the point is that I have a positive number here and a positive number here, and positive numbers are the only kind of numbers we're allowed to take the log of. On the other hand, if we plug in x equal to -5, if I plug it in here, I get log base 3 of -5 minus 4 is -9. And I can stop there. We can't take the logarithm of a negative number, so x equal to -5 is not a solution, whereas x equal to 7 is. So x equal to 7 is our only solution. The reason this is happening is because when you come, so from here to here, if you combine these, if we had started with this, then x equal to -5 would have been a totally valid answer, because -5 minus 4 is -9, and -5 plus 2 is -3, and -9 times -3 is +27. So you get a positive argument before you even take the logarithm, so it would be totally safe. But since we don't have that, we're starting with this, then -5 is not a valid answer. Okay, not too much more. Some gnarly equations here. Solve for x, where you have both sides raised to powers that involve your variable. So we have 6 to the x equal to 5 to the x plus 2. When solving an equation like this, you could use the log base 6 or the log base 5, but the standard practice is to use either the natural log or the log base 10. My preference is natural log because it's less letters to write. So I'm going to say that the natural log of 6 to the x is equal to the natural log of 5 to the x plus 2. Then we're going to use the power rule for logarithm. So we're going to bring down the x in front of the natural log of 6. So we have x times natural log of 6 equal to x plus 2, and I'm going to put parentheses around that, times natural log of 5. Our goal is to solve for x. To be able to do that, we have to be able to isolate all the x terms on one side. To be able to do that, we have to distribute the natural log of 5 to the 2 and to the x, because we always distribute across addition. Multiplication across addition. So I have x times the natural log of 6 equal to x times the natural log of 5 plus 2 times the natural log of 5. I'm going to combine all the terms with x on the same side. So I'm going to write the left-hand side as x times natural log of 6 minus x times natural log of 5 equal to 2 natural log of 5. Then I'm going to factor out an x from the left-hand side. So I'm going to get x times natural log of 6 minus natural log of 5 equal to the 2 natural log of 5. And although you could combine this as natural log of parentheses 6 divided by 5, we typically don't. So dividing both sides by that, we're going to get x equal to 2 natural log of 5 divided by the natural log of 6 minus the natural log of 5. That's how I would prefer to write the answer, but I will point, some people like to write different answers. So an alternative way that's still correct to write this would be bringing that 2 up as the power of 5 and writing it as natural log of 5 squared, and then doing the division here, and 6 divided by 5, so writing natural log of 6/5. That is as compact as we could make it. There's no rule for doing a logarithm divided by another logarithm. So let's look at this next one. Next one is similar. It's actually even a little bit more complicated because we have a power with x plus a constant, a power with x minus a constant here. So same idea. So again, I would say I would choose to use natural log, but I'll do one using just log base 10 instead, just to show you that it's really the same process either way. So let's not bump my camera because it's super sensitive. All right, so again, we're going to take the log of both sides, but this time we're actually using log instead of natural log. And look, it's just terrible because we have to write a whole extra letter instead of ln. So it's log of 4 to the 3x plus 1 equal to log of, I should just say log, of 7 to the 5x minus 6. Bring the powers down in front. So we're going to get, yeah, I'm just going to go this way. Excuse me. 3x plus 1 times log of 4 equal to 5x minus 6 times log of 7. Sorry, I'm squeezing that in just a little bit there. Again, we have to collect the x's, and to do that, we have to distribute the logarithms here. So we're going to multiply the log of 4 by 3x and by 1, and the log of 7 by 5x and by minus 6. So we're going to get 3x log of 4 plus 1 times log of 4, which I'm just going to write log of 4, equal to 5x times log of 7 minus 6 times log of 7. Collect the x terms on the same side, the not x terms on the other same side. So normally I would bring the x's to the left and the other things to the right, but I noticed that if I bring the other things to the right, I get a negative log of 4 minus 6 log of 7. I would rather not have both of them be negative. So I'm going to make the choice to bring my x terms to the right-hand side. So I'm going to get 5x log of 7 minus 3x log of 4. I bring my non-x terms to the right, to the left. Oh my gosh, to the left-hand side. So I'm going to get 6 log of 7, right? Because I'm adding 6 log of 7 to both sides, plus log of 4. On the right-hand side, factor out the x. So you have 6 log of 7 plus log of 4 equal to x times 5 log of 7 minus 3 log of 4. And then divide both sides by all that to get 6 log of 7. It's a lot of writing here. Plus log of 4 divided by 5 log of 7 minus 3 log of 4. And sadly, there's really no canceling or simplifying to do. This is kind of it. And it really here wouldn't make sense to do what we did last time. Because like to simplify this further, you'd have to write this as log of 7 to the 6th power. And 7 to the 6th power is just kind of too large for us to worry about. So this is really how you should leave your answer. If you're asked to find a decimal approximation, you would do it this way. So I'm going to do 6, and I need some parentheses around the top here. So 6 log, where's your log button? Log of 7, close the parenthesis, plus log of 4, close the parenthesis, and now close the numerator parenthesis, divided by 5 log of 7, close the parenthesis, and I put a parentheses around my denominator here, so I'm going to close at the end, and then minus 3 log of 4. And then close the parentheses for the denominator. That should be good to go. We get about 2.34. So notably, x is approximately 2.34. But again, you usually don't do that unless you're asked to do it. All right, I think we're at the last question here. So there are going to be some word questions on this homework assignment. It's good practice for your calculus career because there's going to be lots of word questions in your calculus classes. And also word questions are kind of really like the actual questions we deal with in life. So let's read this out here. A law of physics states that the levels B1 and B2, and that's the levels in decibels, at distances D1 and D2 in meters, from a sound source are related by the equation B2 equals B1 plus 20 times log of D1 over D2, where again, B2 is the level or the intensity level. I think I must write this right, the intensity level at a distance D2, and B1 is the intensity level at a distance D1. So then the question is, what is the intensity level at a distance of 10 meters from the speakers if we know that the intensity level at 2 meters is 100 decibels? So here's the deal. We can kind of make B1 and B2 and D1 and D2 whichever ones we want as long as they correlate. So we know that 2 meters and 100 decibels have to go together. So we could either say D1 is 2 meters and B1 is 100 decibels, and then D2 is 10 meters, or vice versa. So it looks like we're either going to be solving for B2 or B1. Since B2 is already isolated, we might as well make that the level we're solving for. So let's say that B1 and D1 are 100 decibels and 2 meters. So B1 is 100 decibels and D1 is 2 meters. And then we are given the other distance and we're asked to find the other intensity level. So typically with questions like this, word questions where you have an equation and they're asking you to find something, you're almost always guaranteed to have all the other pieces, or at least a way of finding all the other pieces. Here, they're just straight up giving them to us. So we're just going to substitute in the known values and solve for the one that we don't know. So we have B2 equal to 100 decibels. I'm not going to write the units in, plus 20 times the log of D1 divided by D2. D1 is 10 meters, D2 is 2 meters. Again, I'm not going to write the units there. So then we're going to simplify this. It actually simplifies really easily. So our intensity level here is 100 plus 20 times log of 5. And if you were doing this, if you're being asked for an exact value, that's what you would say. Now, the problem here is that that's not super meaningful to me if I actually know what, right? I know that 100 decibels is pretty loud, right? Like I think the concert I was at, the Green Day concert I was at, my watch was telling me that like the sound was going above, I think 80 decibels was safe for hearing. So I was getting an alert every time it was doing that, and it was doing it all the time. I actually turned it off at some point. But the point is that knowing that the intensity level is 100 plus 20 log of 5, well, is that like 110, 130, 150, right? Like what level are we actually at? Is it going to be really dangerous for my ears or just kind of dangerous for my ears? Well, this is where you should use a calculator. So we're going to write this out. We're going to have 100 plus 20 times log of 5. We do that, we get about 113. Okay, so still, I mean, too loud, but it's good to know that this is approximately 113 decibels. Definitely, you should not be exposing your ears to that level of intensity for very long at all, because you will damage them. Anyway, that's all I have. Again, I would highly recommend, if you want more problems to see, to watch the other video I posted and the other video I posted from Grant. Have a lovely weekend. I look forward to seeing you all on Monday.